All right, so Unit 5, we're going to talk about ionic compounds. So when we left off on Unit 4, we were talking about noble gases. Noble gases get their name because they are extremely stable, non-reactive elements. They kind of, hang out by themselves. They don't want to mix with the riffraff. Noble gases also, what we saw, had a filled valence shell of electrons. So except for helium, which we know only needs 2 electrons to fill the first shell, all the other noble gases have 8 electrons in their highest energy shell. In other words, they filled up all their s and p electrons on that energy level. And so if you put these two things together, noble gases are very stable because of this filled valence shell. So all the other atoms try to react in some way to get the same filled valence shell. So all the other elements, atoms, are very reactive to different extents because they want to try to have this filled valence shell. Okay, so just a little bit of a review from Unit 4. Remember that our electron configuration, if we do the noble gas or abbreviated form of our configuration, we can see that an element in the same column all end with the same valence shell organization. So you can see here all the group 1A elements end with S1, either lithium with 2S1 or sodium with 3S1 or potassium with 4S1. So in other words, they only have 1 electron in their highest energy shell. So it's very easy to actually determine the number of valence electrons in an atom because it's equal to the group number if you're using the A representation. So for all the representative elements, you just look at which A column they're in, and that's how many they have. So for example, calcium is in group 2A, so it has 2 valence electrons. Phosphorus is in group 5A, and it has 5 valence electrons. Now, technically speaking, the valence electrons for the transition metals will be 2 because they have the s electrons for the highest shell, and then they go into filling the lower d electrons. But so technically speaking, you would say 2 valence electrons in the transition metals. They have other ways that they can become stable without having to fill their outer shell, and so it's a little bit more complicated, and we're not going to learn how these do it, but we'll talk about them a little bit later. Okay, so a Lewis structure is a very simple representation with the valence shell electrons shown. So very simple. You can see that the group 1A has 1 valence electron, so we have 1 dot. Group 2A has 2, 3 for 3A, 4 for 4A, 5 for 5A, etc. Technically speaking, there's no wrong way to put the valence electrons around the element or the symbol. We like to keep them in pairs, so you can see that we put 2 on each side when it's totally filled with 8A. The way I usually like to put the electrons, the order I like to put them, is to put 1 on the right and then the second one on the right, sort of like they were filling the s electrons, and then I'll go around 1, 1, 1, and then pair, pair, pair to double them up, just sort of following the filling of the p electrons. But really, as long as you get the correct number on your Lewis structure, you're good. All right, so here's something you can take a minute and practice. Write the Lewis structure for each of the elements. All right, you might want to stop it and take a minute and do that, and then check your answer. Okay, so potassium, which happens to be in group 1A, has 1 valence electron, so we just have 1 dot. Antimony is in group 5A, has 5 valence electrons. Barium has 2 for group 2A, and gallium has 3 for group 3A. Okay, so this leads us to something called the octet rule. According to the octet rule, atoms will gain or lose or share sufficient electrons to achieve an outer electron arrangement identical to a noble gas. In other words, all the elements want to have 8 electrons in their highest energy level. Of course, with the exception of helium and a couple of others that can't have 8 because they're only in the lower shell. So the octet rule basically means that an atom wants to have 8 electrons in its highest energy shell or its valence shell. So except for the noble gases, none of the atoms have this 8 electrons in their outer shell. So atoms will bond together in order to get these 8 electrons. And that's where all the chemistry comes from. They're going to bond or react in some way to get these 8 electrons. There's 2 kinds of bonds that we're going to look at in this class. An ionic bond is where an electron is transferred from one atom to another. So in other words, one atom will lose an electron, one atom will gain an electron, and that makes them ions because they're going to be charged particles now, and they'll be attracted to each other. That's what we're going to talk about the rest of this unit. And then there's also something called a covalent bond, which is a sharing of electrons. Oh, I neglected to say the ionic bond is generally, or the ionic bond will happen between a metal and a nonmetal. And a covalent bond, or sharing of electrons, will happen between 2 nonmetals. There's also a third kind of bond that we're really not going to look at in this class called a metallic bond, and that's when there's a bonding between 2 metals. Okay, so let's talk about simple ions. If an atom has acquired a net positive charge or a net negative charge by losing or gaining one or more electrons, they are called ions. So an atom is neutral, ions are charged, either positive or negative. So let's look, for example, at chlorine. We know that chlorine has 7 valence electrons. How can chlorine get 8 valence electrons? Well, it needs one more. One way that chlorine can get an electron is to steal it from somewhere. So what happens is it adds one more electron from somewhere. We'll talk about where later, but the chlorine steals an electron from somewhere and pulls it into its outer shell. So now it has 8 electrons. Remember that electrons are negatively charged. So now the chlorine atom was balanced with 17 protons and 17 electrons. And if we add one more electron, we have one more extra negative charge with 18 electrons. And so overall, the chlorine becomes an ion and has a charge of -1. Negative ions are called anions, and I always remember that they're anions by remembering that anion can stand for a negative ion. All right, now in the case of sodium, sodium only has 1 electron in its outer shell. So one way that sodium could get 8 is to somehow steal 7 electrons, but that just doesn't happen. That's too many electrons to deal with. So actually the best way for sodium to satisfy the octet rule is to lose that 1 electron in its outer shell, and keeping in mind that the shell below it is completely full. So if it loses that 1 electron, it has a full shell. If sodium has 1 fewer electron, it has 1 fewer negative charges, and so sodium will now have a +1 charge because it has lost a negative charge. We call it the sodium ion, and positive ions are called cations. And I usually remember the positive is a cation because the T sort of looks like a plus sign, and so you might remember it that way. All right, this is how we represent the process of losing or gaining an electron. So here, chlorine, we can indicate with a Lewis structure chlorine with only 7 electrons. And then if we add one more electron to it, you see on the right hand side we have Cl with all 8 electrons surrounding it, and we have to put the negative charge because it is a charged particle now. It's not neutral anymore. Sodium loses an electron, and in math we might say if you lose something you subtract it. Well, that's true. We don't usually subtract anything in chemical equations, and so this we represent it here as a sodium atom breaking apart into 2 particles, the sodium ion that's +1 charge, and then the electron that has left the sodium atom. Here's some other examples. So +1 and -1 aren't the only charges that ions can have. Magnesium, which has 2 extra electrons in its outer shell, will have to lose those 2 electrons, and so it will become a +2 ion. Oxygen, on the other hand, as you can see, has 6 electrons. It needs 2 more. So if we add 2 more electrons to oxygen, it will have a -2 charge. I was a little sloppy there. Notice that I did put the 6 electrons. They may not be the same way that I had them represented before, but I do have 6 electrons there. And then I didn't specifically put the 8 electrons on the O-2. I just put the -2 sign. And that's really all you need to do when you have an ion. So these are simple ions because there's just one atom that has become an ion. One more example, bromine acts just like chlorine. It has 7 valence electrons, and so it will gain 1 electron to form an ion with a -1 charge. Okay, so just like we can use the column number to find out how many valence electrons we have, we can also use the column number to find out what the charge of the ions in those columns will turn out to be. So the representative metals, so we know what the difference between the metals and nonmetals are. The representative metals will form ions having the same positive charge as the group number because that's how many electrons they need to lose. Make sure you use the A designation for this. So if you're in group 1A, those elements become a +1 charge. In group 2A, they become a +2, and in group 3A, the metals become a +3. All right, the representative nonmetals will become negative. They form negative ions because they will gain electrons. You can either realize, count the number over from the noble gases, and so group 7A is 1 away from the noble gas, so it has a -1 charge. Group 6A has a -2 charge, and group 5A has a -3 charge. Or if you want to, you can take the column number -8 to get the number. So basically doing the same thing. So group 5A has 5 valence electrons. -8 will give us a -3. Now notice the asterisks, and keep in mind that in group 4, 5, and 6, we're only talking about the nonmetals. The nonmetals will form the charge that is listed here. The metals in those groups, those below the stair steps, actually act like transition metals, and we're going to talk about those a little bit later in this unit. So under the stair steps for groups 4, 5, and 6 will act like transition metals and will not have, they might have a positive charge similar to these, but they won't have a negative charge. All right, so just looking at some examples, strontium is in group 2A, and so it forms +2 ion. Phosphorus, which is in group 5A, makes a -3 ion. I didn't mention group 4A. Group 4A, of course, is halfway full. It needs 8 and it has 4. So it could either lose 4 or gain 4, but we're starting to get into a position where 4 is a lot to lose or gain. And so actually the nonmetals in group 4A will not form ions. They actually form bonds through covalent bonding, which we'll look at in the next unit. That's what I just said. So group 4A could lose or gain 4, but generally they only get their octet rule by sharing electrons. And again, like I just said a minute ago, the octet rule does not apply to the transition metals. In the transition metals and those metals, representative metals that are in the groups 4, 5, and 6. In that case, the charge has to be told to you in some way. And again, we'll talk about that in a little while. So the transition metals and the metals and metalloids in group 4, 5, and 6 somehow have to you have to be told what the charge is. Again, we'll talk about that in a few minutes. All right, so here's just a little picture. So you can see group 1A. You might want to write this on your own periodic table because you'll refer to it a lot. You'll be wanting to know the charges of ions very often. So group 1A is a +1, group 2A is a +2. All of those transition metals have various positive charges that have to be found out somehow, which we'll talk about later. The metals in group 3A, boron and aluminum will always be a +3. Group 4A, carbon and silicon form a zero, don't form ions. Group 5A, nitrogen and phosphorus are a -3. Oxygen, sulfur, and selenium in group 6A are a -2. All of those in group 7A are nonmetals, and so they form a -1. And of course, the noble gases don't form ions either because they are very content with having a full shell. And then notice those main group metals under group 4, 5, and 6, actually a little bit of 3. Those in group 3 will always have a +3, but they might actually have another positive charge also. So you, just like the transition metals, the ones in those ovals, you have to be told what the charge is. Okay, just want to point out and make sure that you realize an ion and an atom are not the same thing. They have very different properties. For example, if you look at sodium metal is a very soft, shiny, very reactive metal. You can cut it with a knife. It's that soft, sort of like butter. Chlorine, the element chlorine, which only exists in a diatomic molecule, so but it's only chlorine. On the right, you can see is actually a green gas. It's poisonous. They often use that to make bleach or chlorinate water, but it's a very corrosive, poisonous gas. However, if you take a sodium ion and a chloride ion and put them together, what you get is table salt. Table salt's very unreactive and very stable, and so you want to make sure that if you're referring to the ion that you write the charge as part of the ion. The element is the element and the ion has the charge. Just for your information, you can stop this slide and look at those. I'm sure some of these you already know. Some biologically important ions. Calcium ion in your bones and teeth, iron in your blood, potassium inside the fluids inside your cells, sodium fluids outside of your cells, magnesium also in bones, and so forth. Bicarbonate controls your acid-base balance in blood and comes from carbon dioxide. All right, we can write an electron configuration for an ion. In this case, on this slide, the anion. So remember that anions add electrons, and so all we have to do is for chlorine here, you can see the electron configuration for chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. Well, just like we suspect, chlorine gains 1 electron to fill the outer shell, so if we add 1 more electron to it, it will add to that 3p subshell, filling the 3rd shell to complete the shell. So the configuration for chlorine ion with the -1 charge is 1s2, 2s2, 2p6, 3s2, 3p6. Below you can see sulfur, the same thing. Sulfur has to gain 2 electrons. Where does it put those 2 electrons? It fills out the 3rd shell. Notice that the highest energy shell is now filled. And also, you might notice, we'll look on it in the next slide, that those electron configurations now look like noble gas configurations, or follow a noble gas. Cations, because they lose an electron, we can write the electron configuration for the cation by just removing the number of electrons from that element. So you can see here potassium has that 4s1 electron. The 4s1 electron is the one that's going to be removed. So if we take that away, we get 1s2, 2s2, 2p6, 3s2, 3p6. And you might notice that looks familiar from the last two. And calcium, which loses 2, you can see we take off those last 2, the 4s2. And again, we have the calcium ion configuration that also ends in 3p6. So we have the full shell underneath. So all of these elements that we've been talking about and ions are actually considered isotonic to each other. So here you have the chlorine atom ending with 3p5 and then the chlorine ion ending with 3p6. We have the potassium atom ending with 4s1. If we take that away, we have potassium ion ending with 3p6. Notice that chlorine ion and potassium ion both have the same electron configuration as argon, the closest noble gas, which was the goal in the first place. They want to have that noble gas configuration. You can also look, sulfur, if it gains 2 electrons, also has that same noble gas configuration of argon. The term that we use for this is isoelectronic. All 3 of these ions are isoelectronic to argon. They all have the same electron configuration. Now, keep in mind, it doesn't mean they have changed to argon, because chlorine still has 17 protons, potassium still has 19 protons, sulfur has 16 protons, argon has 18 protons, so they all have a different number of protons. So remember, that's what gives an atom its identity, but they all have a same electron configuration, and so they are all much more stable. Just another example below, the oxygen ion O-2 and magnesium +2 both are isoelectronic to neon. All right, so now that we have ions, remember that opposites attract, and so if we have an ion that has a positive charge and we have an ion with a negative charge, they will be attracted to each other. Again, remember that the metal is the one that loses the electron, the non-metal gains the electron, and so technically speaking, in this case, a sodium metal, if we reacted sodium metal in chlorine gas, the sodium will give the electrons over to chlorine, and then we'll have a sodium ion and a chloride ion, and then they'll be attracted to each other, and that is what an ionic bond is. It's when 2 ions are attracted to each other. One thing that you might notice here, that when a sodium and a chloride, we'll talk about names in just a minute, when they're attracted to each other, in this case a +1 and a -1, the charges will cancel each other, and that's going to be an important feature that we'll look at on the next set of slides. Okay, so now once we have ions, we create ionic compounds, and ionic compounds are substances formed when ionic bonds form between positive ions and negative ions. Again, it's a metal that forms the cation and a nonmetal that forms the anion. If we make an ionic compound that has only 2 kinds of elements, we call this a binary ionic compound. So here are some examples of binary ionic compounds. Table salt, with just NaNCl. Rust, which is iron oxide, has iron and oxygen. Sapphires and rubies are aluminum oxide, which is just made up of aluminum and oxygen. As we'll see in a little while, there are some ionic compounds that have more than 2 elements, but the first ones we're going to look at are these binary ionic compounds. And so that ends this first set of slides, and then You can come back on and see the second set of slides later. Okay, thanks.